Good evening, Professor.
How are you doing?
All good, Professor. How about you?
Right?
Happy first day of the spring.
Pardon me?
It's the first day of the spring. Happy first day of the spring.
Oh, yeah, I never thought of that. Yeah, you're right. That's true. Yeah, and the weather is here. The spring weather is here. Finally got something warm. Okay. Mhm. We continue the elements of variational calculus. Last time we derived that if L is a function of Q, column vector Q, column vector Q dot and T, and Q are all independent, then the variation of L equals to 0 condition, variation of S. Variation of S, which is variation of integral from T1 to T2 of L of Q dot T dt equals to 0 condition of extremality of S, means either minimum or maximum, given that Q of T1 equals to, let's call it A1, and Q of T2 equals to A2. The tilde underneath means column vector, by the way. It's a column vector A1, AN, etc., right? Then this condition, leads to integral of T1 from T1 to T2 of dl over dq minus d over dt dl over dq dot, column vector, dq dt plus, hang on a second, plus the let's see. We're gonna do this dl over dq. Let me just say dl over dq dot, and we have this one as the dv, and this one u. So it has to be the other way around, plus dl. That's over dq dot times d over dt of delta q. No, so times delta q. I think that's what it is, right? You write it down. Integral of dl over dq dot dt will be equal to dl, oh, sorry. dl over dq dot times delta q dot, which is d of dt of dq dt would be, this one was differential, and this is u, and that's dv. So that became uv dl over dq dot times delta q. All right, that's fine, yeah. Minus, all right, okay, got it. Just a second. That's exactly what I wrote here, and that's from T1 to T2. And that is supposed to be equal to 0. This delta S equals to this. And since delta Q of T1 equals to delta Q of T2, the variation of Q at the ends is 0 because the Q is fixed at the ends. This leads to, and this is true for any delta Q. Then we have our equations dl over dq minus d over dt, dl over dq dot equals to 0. All right. Does it make sense so far? You have any questions about this one so far?
It makes sense.
All right. So now, what if we have only at one end boundary condition for Q? Say we have Q of T0 equals to A, but Q of T1 is variable. How do you solve this problem then? Well, look at these equations. Let's call this equation to be equation 1. Then equation 1 becomes integral from t0 to t1, just like we were before, dl over dq minus d over dt of dl over dq dot times delta q dt, and we have plus that extra, so, all right. Plus the extra term here, right? Okay. Remember, this term disappeared. Now, only one of them disappeared, the other one stayed, plus dl over dq dq dot, sorry, times delta q, and that's at t1, both of them at t1, sorry, at t1, both term, supposed to be equal to 0 for any delta q that is 0 at t naught. Here's our logic then. The delta q is arbitrary, and the delta q here is arbitrary from this one, since delta q at second term is independent of delta q in the integral. To get 0 for any delta q, we need the following. First of all, we'll have this bracket equal to 0, d over dq of L minus, that's the first term, right? d over dq of L minus d over dt of dl over dq dot equals to 0, and plus another condition, the extra term has to be equal to 0 as well, plus dl over dq dot at t1 has to be equal to 0. Since delta q is arbitrary. This is what is called, let's see, I believe this thing, natural boundary condition. Whereas the whereas q of t naught equals to 0, sorry, delta q t naught q of t naught equals to a, that's called essential boundary condition. This one is stipulated at the beginning. at the onset. Well, this one comes from physics of the problem, from mechanics. All right. Let's look at an example. I think, can you make an example there? Bar, it's cross-section area A and E, Young's modulus, right? It is subject to distributed force. That's Q, not Q, sorry. W X. This is L. This is X. Should I use W? Yeah, I guess so, right? Okay. And the variable is displacement is U of X. Strain, epsilon X equals to du over dx. Stress, sigma X equals to E epsilon X, and that's going to be E du over dx. Potential energy, what letter should we use? V, I guess, right? V equals to 1/2 of integral from 0 to L of sigma X epsilon X times d volume. And that's going to be 1/2 of integral E d squared U over dx squared. Sorry. First, du over dx squared, the squared from both of them. And the element of volume is A and dx. That's integral from x1, from x equals to 0 to x equals to L. All right, so far so good. Which is going to be, assuming A and E are constant, we're going to be A E over 2, integral from x equal to 0 to x equals to L of du over dx squared dx. Hang on a second, let me think about it for a second. Okay, that's the elastic energy. The elastic potential, that's something that you might have heard, maybe not. It's going to be E equals to the potential energy minus summation of Pi ui, and P are the forces, and these are displacements. So in our case, it will be equals to 1/2 of integral from 0 to L of, let's see, AE over 2, 0 to L of du over dx squared dx minus integral. And we have this load, let's see, on a short segment, the load will be W times dx, all right? Integral from 0 to L of W of x times u and times dx. The result is the elastic potential E equals to integral from 0 to L of AE over 2 du over dx squared minus W of x u of x dx. The condition for equilibrium is that E goes to minimum, which is familiar to us, all right? The boundary condition is only one. The u of 0 equals to 0 where it's fixed. U of L, we don't have any condition there, all right? Therefore, to get to the minimum, you need the following. You need to have first dl, let's say this is the L, right? dl over du will be minus W of x. dl over dux, that's the ux, equals to AE over 2 times 2 du over dx, which is going to be AE du over dx. D over dx of dl over du of x equals to d over dx of this piece AE du over dx, assuming constant, but they don't have to be. It's going to be AE d square u over dx squared. So the differential equation, equation 1, as part of this one will be AE, just a second, did I? No, sorry, I missed this one. Minus W minus AE d square u over dx squared equals to 0. That's equation number 1. Equation number 2, let's look back at what we obtained here, right? At the right end, we'll have dl over dq dot at t1 equals to 0. That means in our case, d over du x of our thing, which is a over 2 d over dx squared ae over 2 du over dx squared minus w over x u over x, and that at x equals to L at the right hand should be 0, which is going to be ae du over dx at x equals to L, and it should be 0. That's the natural boundary condition. So to solve this system, we'll have the two equations. The first equation was, we'll make a plus of everything. So we'll have ae d squared u over dx squared plus w equals to 0. W is a function of time. And then we have this one. A and E are 0, so we'll have, well, let's write it down. ae du over dx at x equals to L is 0. U of 0 equals to 0, that's the natural, no, that's the essential boundary condition. I always confuse those names. Essential boundary condition. What it tells you actually that it's fixed, right, at the left end. This one is going to be the natural boundary condition. What does it tell you physically? This one is the strain in the x direction. This is going to be the stress, and this is going to be the force. It tells you that the force at right end is 0. So that's the natural boundary condition. The other one was essential. All right, does it make sense to you?
Yes.
Any question of this problem? All right, let's continue then. Let's see what my notes are. All right, got some examples from your text. Now we'll talk a little bit about constraints. Are you guys done with this page? Yes, no?
Yes.
Okay. Constraints. This I'm going exactly by the book. Suppose, oh, just notation slightly. Suppose we want to minimize S and that's equal to integral from x naught to x1 of f of x y y dot y prime, sorry. Y prime dx. But this time, the y are not independent, given constraint. Integral from x naught to x1, same limits, of g of x, y, y prime dx equals to c. That's a constant. And you know what? Should we take let's make this a column vector. And this is all column vector. They're all functions of x, all right? So you can, then we try to minimize this given this constraint, right? And of course, the minimum will be the delta s will be the integral from x naught to x1 of df over dx minus d over dt df over d, sorry, not dx, I'm sorry. Over dy as d over dx here. That's the dx. Let me just clean it up a little. This will be dy prime delta y dx equals to 0. But for not all delta y's, but only for those that satisfy condition 2. Again, let's call the column vector, right? Okay. We have how many? We have the dimensions of delta y. Delta y is delta y1, etc., delta yn. and dimensional. But not all of them are independent. Okay. We have that they have to satisfy this condition. So how do you solve this? You solve it like this. You solve it similar to calculus, you do like this. You create a function f star, and that's going to be f plus lambda times g, where lambda is called Lagrange multiplier, something that we don't know the value of. So that's an unknown one, right? Okay, we still don't know this, right? And then we form the condition. We'll have summation. Remember, we had that summation there. Remember, I wrote it down like this. That should be delta. So it's a summation, right? So it's this one. Do you understand what I mean by the delta, by the dot here? If you call this one to be tau, right? So tau dot product with delta y will be tau 1 times delta y1 plus tau 2 delta y2 and plus etc. plus tau n delta yn. Okay, is it clear now? Yes, no? Okay. So we form this function, and then we'll write down not a sum. It's going to be actually no. So we have then the integral. Let's call it tau k, call vector delta y k summation of from k 1 to n. This integral from x0 to x1 equals to 0, where tau k is equal to df star over dy plus lambda df star, sorry, lambda dg star over dy minus d over dx of df star over dy prime plus lambda dg star over dy prime that's a tau k. Now this is delta 1k, right? Okay. So we have this equal to 0 but not all of them are independent. But here is how we can do. For example, for k equals to n, solve for lambda. Okay. And that will be so once lambda is found, then the tau n then is 0, okay, for that lambda. And so we then have the summation from x naught to 1, summation this time for k equals to 1 to n minus 1 of tau k delta yk equals to 0, but this time the constraint is used up. Constraint is gone. All right. And the delta yk, with k being there should not be a column here, sorry. Delta yk equals to 1 to n minus 1 are independent. All right. So then we require, so then we have tau k equals to 0, with k being 1 all the way to n minus 1. To summarize it, we solve the condition that tau k equals to 0 for k equals to 1 to n, and also find the lambda, and then the g of x, y prime all together are satisfied. All right. So solve this system together. All right. Okay. All right. That's the constraint thing. Now let's have an example. Problem number 314. A particle of mass m is constrained to move on the surface given by the following equation. You know what? No, I'll take the 312 first. So that will be more proper. This is also easy, but we'll do the 312 first. $311, sorry. Find the extremal of interval from 0 to 1 of y prime squared dx given constraint constraints are y of 0 equals to y1 equals to 0, and the g constraint, which is interval from 0 to 1 of y squared dx equals to 1. Okay. Form f star, and that will be y prime squared plus lambda y squared. Write the equations. Df star over dy equals to 2 lambda y. Df star over dy prime equals to 2 y prime. D over dx of df over dy prime equals to 2 y double prime. So the conditions will be that we have 2 lambda y minus 2 y double prime equals to 0. And in addition to that, we have that integral of y squared dx equals to 1. Well, let's call this one to be 3, and this is 4. Let's try to solve it. Y double prime equals to lambda y. We take y equals to e to the r x. Y double prime will be r squared e to the rx. So we have the r squared minus lambda. You know what? I think it's easier to call this constant not lambda, but make it lambda squared, right? Things will be simpler. Let's call it like this. So then we have r squared minus lambda squared equals to 0. So r equals to plus minus lambda. And the y equals to a e to the lambda x plus b e to the minus lambda x. Well, y of 0 equals to, what was the condition there? 0. That means a times 1 plus b times 1 equals to 0. So b equals to minus a. Y of 1 equals to 0. That means, and by this one, y equals to a e to the lambda x minus e to the minus lambda x. And then this will be y of 1 equals to a times e to the lambda minus e to the minus lambda. Yeah, somehow that doesn't fit the bill. Something is missing here, right? Okay. I think I know what's missing. The lambda could be a function, right? That's the whole thing. Lambda is a function of x. Yeah, I forgot to bring this up, right? Okay. That's a known function of x, right? So df over dy, that's true. But d over, all right, so this is correct. Dy prime. Yes, so we cannot do this, so we have to erase this one for the time being. Lambda is a function of x as well, right? Okay. It's an unknown function, just like y and y prime, right? Okay. Let's see what I can do with this one. So we have this condition. This one, we have this one, and we have y of 0 equals to y of 1 and equals to 0, right? Hmm. y prime equals to lambda squared y. Okay, y equals to e to the rx, all right? While double prime equals to r squared e to the rx, that's correct. But lambda is a function of x. So we'll have the r squared e to the rx equals to lambda squared e to the rx, all right? So r squared equals to lambda squared. R equals to plus minus lambda, but lambda is a function of x, all right? So the result is that y equals to a e to the lambda x, that's correct, plus b e to the minus lambda x, but lambda is a function of x, all right? So y of 0 equals to 0. You just double check if my signs are correct. Okay. This is correct, this is correct. Y of 0 equals to 0, that means a times 1 plus b times 1 is 0, so we get the same condition with the lambda is a function of x, so b equals to minus a. And so y equals to a times e to the lambda x minus e to the minus lambda x. Yeah, we got some kind of a stupid thing. So y of 1 equals to 0, unless it's a typo here, right? And that will give you that a times e to the lambda minus e to the minus lambda is 0. Therefore, a is 0 and y equals to 0, right? So that's kind of a silly answer. That makes no sense. Okay, I'll try to clear it up. But let's go to the next example from the book. All right, there is another condition, and that's the following. What if we have S equals to L of U prime and X, Y and Z, all right? And we have dx, dy, dz. And that's integral over the domain. So in other words, U is a function not of one variable, but of 2 or 3 variables. In this condition, in this case, we have the following. The Lagrange-Euler equations become dl over du minus d over dx of dl over du sub x minus d over dy dl over duy minus d over dz dl over duz. And the u sub x is du over dx. But by this is partials. The u of y, u sub y equals to du over dy, and u sub z equals to du over dz. Okay. That's the Lagrange equations where the u is a function not of one variable, but of several independent variables. Right? So now we'll have an example of this sort. Example. Write Euler-Lagrange equations for this functional, for S equals to integral 1/2 of integral from T0 to T1, and inside you will have double integral over some domain D of rho, pardon me, of rho d over dt squared minus c squared du over dx squared plus du over dy squared. It's double dx dy that's this integral, and then we figure bracket ends, and then we have integration over the time dt, and we need to run it to a minimum. In this case, u is a function of 3 independent variables, x, y, and t. So we use these conditions. This is the L. We have dl over du equals to 0. U is not explicitly here. dl over du sub t, that's the u sub t, equals to, well, we have the 1/2 in front, right? Let's not forget. So we can put the 1/2 inside, and now 1/2 will disappear. This is going to be rho u sub t. Right? And now d over dt, d over dt, oops, d over dt of dl over dut will be rho utt. Then we say dl over dux equals to c squared du over dx. The two got canceled by 1 here. So d over dx of dl over dux equals to c squared d squared u over dx. And very similar to this, d over dy of dl over dy will be c squared. By the way, this is a minus. Let's not forget it's there, right? I was going to minus c squared d squared u over dy squared. The result of all of this, we have rho utt rho utt minus c squared times uxx plus uyy equals to 0. Coincidentally, do you know what this equation describes? This is equation describing vibration of thin membrane, like a drum head. Of mass density rho per unit area and the c squared is T divided by I don't remember what is divided by. I think it's by rho. It's right like this. I think that's what it is. And T is the tension in membrane per unit length of perimeter. So in other words, if you take this membrane and supposedly it's attached right here, that's a very thin membrane. If you look at this one, if you look at this one right there, right? And if you look at this one being 1, you will have the force will be, that's the T. All right, let's see. Cover this, we discuss this. Your homework is due, your current homework is due when?
It was Monday.
This Monday it was due?
Yes.
Okay. So I'll probably give you a quiz, take-home quiz. Probably this Monday, I'll put it in there, no. You want to have it over the weekend, right? So maybe I'll put it there this Friday. And it will be due Wednesday, will be due Monday. Okay,
The quiz, is it chapter 1, 2, 3, or
not chapter 3, only the chapters that are covered by the homework,
homework 1 to 3, right? Okay.
1 through 2. I don't think the homework is in chapter 3.
No, it was chapter 2. Yeah.
That's why chapters 1 and 2. Okay. So it will be 2-3 problems similar to homework problems. All right.
All right, Professor. Thank you.
Thank you.
And if you have any questions, remember I'm still having the office hours Fridays, 3 to 5. You can still ask questions on the homework to prepare. Okay.
Thank you, Professor.
Okay. All right. All right. We'll cover it and see. Have a nice weekend.
You too. Have a nice weekend.
Thank
Bye.
you. You too.